Hey everyone, welcome to University of Winnipeg Chemistry 1112, Chemical Kinetics, Unit 13, Lecture 3. I'm Dr. Carroll, and I am pumped today to talk about two sections, 13.5, linking mechanisms and rate laws, and 13.6, the effect of temperature on rates of reaction. We've already talked a bit about reaction mechanism, a series of elementary reactions describing how a chemical reaction will occur, as we see on page 635. So I'll just reading here. And then the sum of the individual steps gives the overall balanced chemical equation. Sometimes a step may occur more than once in a mechanism. Yeah, that can happen too. You experimentally get the rate law first, and then you tell stories. You create reaction mechanisms to jive with the experimental data. If the rate law matches the experimental rate law, it's a possible description. Again, you need lots of information to get it all. We talked about bimolecular, unimolecular, fine. And so here's some mechanisms and some rate laws. So if we have here overall 2NO2 goes to N2O4, one mechanism might be NO2 plus NO2 goes to N2O4, and so the rate would be K times NO2 squared. Here, maybe it forms 2NO plus O2 that occurs via a two-step mechanism. So the rate is proportional to the concentrations in the rate determining step. So not to NO3 or NO, just to NO2. Then we have another one and a few other examples. Again, the slowest step. The rate determining step is not always the first step. If it is, then our calculations are a little easier. There's less stuff to talk about. In fact, all the table we just looked at, they were all the rate determining step was the first step. If there's only one step, well, yeah, that is the first and only step. Okay, so let us see an example here. CO plus NO2 goes to CO2 plus NO. So that might be happening in one fell swoop, or maybe not. In one mechanism, you can go get a activated complex to get CO2 plus NO. That's all happening in one step. Another possible mechanism, you have two NO2s hitting each other. So then you get an NO2 and an NO. And then one of those, sorry, an NO3 and an NO. Then one of the NO3s hits the carbon, so you get back to an NO2 and a CO2. So the NO3s cancel out. So there's two possibilities. Experiment helps us decide what is the best one. The question doesn't ask for that though, it just asks what is the predicted rate law. So in the one-step mechanism, the rate law would just be K times CO times NO2. It's just one step. In the second step, it would be the rate would be K times NO2 squared. NO2 times NO2, second order overall. Okay, so this reaction makes sense. Yeah, it does. Now, experiments show the result is second order in NO2. Okay, so then the second proposed mechanism is the winner here, but you'd need to know that beforehand to make that determination. Okay. Agreement with the rate law does not prove the second mechanism is the correct one. However, because other mechanisms we haven't even looked at may predict the same rate law, it is one strong piece of evidence that supports this particular two-step process. Okay. Practice exercise. So the rate law would be K times, well, you have 2 butadiene molecules. So the rate would be K times the concentration of butadiene times the concentration of butadiene. Okay. So now the one that's a bit trickier here, where you have some years we don't talk about this. Some years we put it in. I don't know whether it's going to be in or not, so I'm going to be on the safe side here and discuss it. Okay, so rate determining where the first step is not the slowest step. Yeah, that is true. The first step is not the slowest step. The first step is not the rate determining step. The rate determining step comes later on. The rate determining step, RDS, is short for rate determining step, occurs after one or more faster steps. So the reactants in the earlier steps may or may not appear in the rate law. We'll see how that works in a second here. Sometimes you get orders which are fractions, negatives, greater than 2's, all sorts of things a little bit out of the ordinary, which signal that a faster step happens first and then a slower step. So here's an example. We have H2 plus Br2 goes to HBr, two of them. And it turns out that this is not a simple process. You don't just take a hydrogen and bromine, smash them together, but rather there's this square root of Br2 for the rate law. So for the first step of the mechanism, for this reaction to be rate determining, it would have to include a half molecule of Br2. There isn't such a species, so the first step can't be rate determining. Instead, something else has to be rate determining. So let's see what happens here. We have hydrogen and we have bromine. So here's what they say happens. It's on page 638. So we have the bromine stretching, and you get 2 Br atoms. And then very quickly, the Br atoms approach and form a Br2 again. So you say, well, not much happened. Well, but you do have a Br atom also approaching. I mean, you have all sorts of things happening on, but another Br atom approaches a hydrogen, and you get a rearrangement of bonds. You get an HBr and a Br, and so now you got an HBr and an H. You got an H, then you're reacting with another Br2, and you got another HBr and an H. So that's if you like pictures. If you just like using the symbols, follow with me here on page 638. So the reaction begins with the dissociation of Br2 molecules into Br atoms. So this is step 1. And the K with the little 1 is the rate constant for that. Almost all of the Br atoms produced in the first step simply recombine to regenerate Br2 molecules. So the -1, and some people do it differently, they would call this K2, but K -1 means the reverse process. Okay, so it's a reversible reaction. We're hinting about the chemical equilibrium chapter, which is coming up a few chapters from now. So this reversible reaction occurs rapidly in both directions. We can combine them into a simple expression. Br2 goes to 2Br. So we got K1 going to the right and K -1 going back over. So this is a fast reversible process. Occasionally, a bromine atom reacts with a molecule of hydrogen to form one molecule of HBr and a hydrogen atom. Now this step takes a bit more time, so because you're going to be forming an activated complex and then breaking a hydrogen bond and forming an HBr bond. So that is our second step if we've combined K1 and K -1 to the first step. And that turns out to be the slow rate determining step. But then we have to consume that hydrogen atom, monatomic hydrogen atom, which otherwise is really, I mean, it's an intermediate really, so it can't be overall. It has to cancel out. So it's going to react with a Br2 molecule, and that happens quickly. So you get an HBr molecule and a Br atom left over. So 4 steps. The first 2 are combined. Let's see if it's satisfactory. So I hope we're going to annotate. There we go. Let's write all of them going in the same direction and then see what happens. So Br2 goes to form 2Br. 2Br goes back to form Br2. Br plus H2 goes to HBr plus H. H plus Br2 goes to HBr plus Br. So if I did an RPIC chart here, so my reactants are hydrogen and bromine. My products are HBr. My intermediates are Br and H. I don't have any catalyst here. We shall get to catalyst in a second. Oh, the phone is ringing. I hope somebody answers that phone. Maybe I got free pizza. Oh, no, I don't think that's free pizza. So I'll take that later. Okay. Let's keep going here. Okay, yeah, that's not free pizza. Why would anyone call and give you free pizza? That would be a good question. That's the first question on your exam. Why am I getting free pizza in this screencast? Okay, here we go. So that's my net reaction. I like to call it the overall reaction because overall, once you cancel things out, you're left with something. I guess net reaction. Should I call it net reaction from now on? Change my ways of thinking? Sure, why not? So the net reaction is the sum of the 4 steps, and it was the 3rd step that was decreed to you to be the rate determining step. Okay. Now, of course, they decided to call this one K1, K minus 1, K2, and K3. So we're going to use K2. Fine. I've seen other books go K1, K2, K3, K4, but this is okay. So the rate is K2 times K2 times BR times H2. The thing is, BR is an intermediate. It's very hard to measure the concentration of BR. In fact, you aren't putting BR into the system. So you want to find a way to not use BR monatomic in the rate. So we have to do something here. And what we do is this. We know that the first step, or the first combined step 1 and step 2, really are as if a dynamic equilibrium exists. So Br2 molecules decompose, but then Br atoms concentration quickly become large enough to recombine to go with Br2. So we have this equality, which is teasing again the whole concept of equilibrium. So let me just rewrite what we have here. Rate is K2 times, times Br times H2. Okay, and now we've made this equality between Br2 and Br squared. So K1 times Br2, right, going forward, is K minus 1 times Br squared, right? If we go back up here and look at the rate for the first step, it's K1 times Br2, and then the step going the other way, it's K minus 1 times Br, so K minus 1 times Br squared. So what I'm going to do now is I'm going to solve for Br. So Br is the square root of K1 over K minus 1. And I also got a Br2 in there. Okay, because I can't measure Br, it's an intermediate, but Br2 I can measure, so then I can write it as rate equals K2, then I got an H2 at the end here, and my Br I now substitute in, the book wants to use exponents here, so K1 to the 1/2 over, that's a minus 1, K minus 1 to the 1/2, all times Br2 to the 1/2. And some books then take all this combination of K's within the elementary steps in the reaction mechanism and then call it K observed or K experimental. So rate becomes K observed times H2 times Br2 to the 1/2. So that's how I end up getting a fractional exponent. And I've now got this rate law where I can control the concentrations of the reactions that are put in. Hydrogen, diatomic hydrogen molecule and diatomic bromine molecule. So it's a little bit of fancy substitution, but there you see where the equilibrium comes out of. Some people call this a steady state equilibria system. So there's some other words for it. And this just shows what I just did. So I'm not going to talk about it again. Okay. So let's try another one here, or one or two. Example 1310. I just get the right page here. Okay, nitrogen oxide, or nitrogen monoxide, converts ozone into molecular oxygen. Is this one that's going to have a catalyst coming in? No, we're going to get into that later. Experimental rate law is K is O3 times NO. So that looks like it might happen just in one step. So mechanism 1 looks like it's the winner. Now you got to always check, because we could be sneaky and not have it add up nicely to give us what I want. O's cancel, they're intermediates. NO3s are intermediates. I got an O3 and an O3. So I got 2O3 plus 2NO goes to 2O2 plus 2NO2. Okay, well, I could divide everything by 2 and I would get the same as the other one. So that's interesting, why they didn't put halves in front of all of them. Let's go on. Let's see, mechanism 2, we got fast reversible, so we got K1 times O3 equals K minus 1 times O2 times O, and then we have the slow step, so rate is K2 times NO times O. Now O is an intermediate, so I've got to isolate for O, and I'll get rate then is K2 times NO, isolate for O, so that becomes K1 O3 over K to the minus 1 O2. That looks a little fishy, doesn't it? That doesn't look like it's going to be the answer there. That's not NO times O3. We got an O2 in there. Then the third one, rate equals K3 times O3 times NO. That looks like that's the winner. Let's see what we have here. Really? Gives the correct overall stoichiometry. Mechanism 1. Why do I have it all multiplied by 2 then? Mechanism 2 is not going to be good. Inconsistent. It actually has a rate that's inversely proportional to the amount of oxygen. Mechanism 3 is good as well. So 1 and 3 are the answers. Okay, you need more information to get what the real winner is. Mechanism 1 is less likely than mechanism 3, it says, because the products are less stable than O2 and NO2. So mechanism 3 is a bit more stable. I still don't like the fact that we got 2's in front of everything here, but the book is just ignoring that. So if I really had to choose the winner, I would go with mechanism 3, as the book did say that, because O2 and NO2 are more stable if you have to make a choice. Okay, let's try practice exercise 1310. So in my first step, I'm going to get, well, you know what? Yeah, okay. Let's change it up a bit. Let's get the rate law first, and then see what the net reaction is. So we would have K1 all gas phase times NO2 times O3 equals K minus 1 times NO3 times O2. And then we have a slow step. So the rate is K2 times NO3 times O2. Okay, now let's see what our net reaction is, because that'll help us decide what goes in to our rate law. So does anything cancel out here? NO3 cancels out, so it's an intermediate, so it better not be in our rate law. Does anything else cancel out? No. So you get 2 NO2 plus O3 goes to N2O5 plus O2. Okay, so NO2 and O3 are the reactants, N2O5 and O2 are the products. You did see how you can have products in the rate law, which is interesting. So if we didn't do anything, we would say the rate is K2 times NO3 times O2. But NO3 can't be in there because it is an intermediate. So we have to isolate for NO3. So you're going to get rate is K2 times O2 Why do I have rate as K3 times NO3? That's not O2, that's NO2. That should say NO2. Okay. So K2, now the NO3 is going to be K1, NO2, O3 over K minus 1, O2. Okay, and then I got another NO2, so that's NO2 squared. So this can all be written as K observed. So rate is K observed, NO2 squared, O3 over O2. So a bit more complicated than some of the ones we look at most of the time on a test. The questions will have of these kind will actually have the slow step first, and we don't really talk much about fast reversible. But if you ever come across one, this is the way in which you do it. Okay? You can read about ozone on your own and the reactions, and that's great. Okay, so now let's jump ahead to 13.6, reaction rates and temperature. Okay, let's get to the right page here. Page 643. We have temperature also affects the equilibrium position of a reaction. Yeah, we know that. That's Le Chatelier's principle. We're going to get to that. So, as you can imagine, the greater the temperature, the faster a reaction happens. And this is just a bunch of information. Oh, I guess I should talk a little bit about something that you remember from last year, which is potential energy profile. Okay, so let's talk about that here. PE diagrams or profiles. Okay, so you can have the energy in joules or kilojoules, progress of the reaction, also called the reaction pathway or the reaction coordinate. Those are other names for it. We're going to end up talking about temperature in a minute. This is just a bit of a build-up before we get there. So we have the stuff on the left are my reactants, then my products, then at the top of the hill there's this most unstable arrangement of colliding particles, which is called the activated complex. And so you have here, what is this? Nitrogen monoxide and ozone smashing into each other to give you nitrogen dioxide and O2. So you see at the top here, you have which looks like a hopefully effective collision, which means it can form products. So you have the nitrogen and attacking the oxygen. So there's the proper orientation. Then you get this rip and you get the oxygen, and then NO2, it rearranges its geometry a little bit. So there's the products. The difference between reactants and products in this drawing is delta H of the reaction, and it's exothermic because the products are less energetic than the reactants. Something you might have remembered last year is delta H of the reaction is potential energy products minus potential energy reactants. And it can also be written as the forward activation energy minus the reverse activation energy. The forward activation energy is from wherever the reactants are, wherever you choose to have them on the potential energy profile, up to the top of the hill. So that is EA forward. If it's me, I'm not the top of the hill, I'm over the hill. And from the products, from the products to the top of the hill, that is EA reverse. See, what happens is the O3 and NO hit each other, boom, boom, boom. Then the products, well, they start hitting each other and they go back the other way. So you end up with these competing reactions happening until equilibrium sets in. Okay? So the rates at which these occur are the same once equilibrium kicks in. But before it kicks in, we have to look and we see that actually you're forming product more quickly because the hill is lower. The barrier is lower on going from left to right in this exothermic example. Delta H is negative, exothermic. Then going from the right-hand side back to left. Kids get upset about this. They say, products, it's products. How can they go back to reactants? They're being produced, not producing things. Well, sorry, the words just got blurred together. And I like to talk about going from left to right, going from right to left. So both of these things happen. And you see that if I take EA forward minus EA reverse, I get delta H reaction. If I was looking at an endothermic example, well, then the reactants would be lower down than the products. My delta H will be positive. I have a net input of energy into the system. I still have a forward activation energy from the reactants to the activated complex. So that's EA forward is there. And from the products to the top, that's EA reverse. So the activation energy is the minimum amount of energy needed to form an activated complex, right? And there are ways to lower the activation energy, which we'll learn about in our next lecture, using a catalyst. So catalysts can lower the activation energy, and changing the temperature will allow more molecules to have at least the activation energy. To a forced approximation, though, be careful, temperature doesn't change the position of the activation energy. It just allows more particles to have that activation energy, to collide effectively per second at a greater frequency than at a lower temperature case. Concentration also does not change the activation energy. E-act is another way to write activation energy. Our book writes it as E lower a, which is fine. And if you just say activation energy, if you don't say forward or reverse, then the assumption is you're talking about forward activation energy. Okay. Again, I'm not going to review all of these or do numerical examples because you've seen them lots in grade 12. Anyways, at the moment, maybe later I will. Okay. Activated complex. Yeah. Okay. Great. So now what about temperature? Here I have a Maxwell-Boltzmann distribution curve. We'll just call it a energy curve. And we have a plot here of fraction of particles or number of molecules versus molecular energy. And so we have a activation energy. And I'm just going to fix it there. And let's look at this curve T1. See, all the particles are moving around. This reminds you a bit of the gas laws we did a few chapters ago, chapter 2, where you have a cluster around most probable speeds, most probable kinetic energies, and there's some slowpokes, and then some speed merchants, some speed demons. And anywhere under the curve, those are the ones which can cause an effective collision. So at any temperature, some fraction of molecules has the energy greater than the activation energy. At a higher temperature, well, the whole curve is going to skew to the right. And if I'm looking here as EA, I'm going to have more molecules with energy greater than the activation energy. So at higher temperature, there's a greater fraction of molecules that can cause product to form. Now, what's this business here? EA prime is greater than EA1. Why are they even saying that? At higher temperatures, more molecules have E greater than EA. For larger EA, a smaller fraction of molecules has E greater than EA. Okay, big deal. They're just saying if you have a really large activation energy to begin with, then increasing the temperature isn't going to be as dramatic an effect as if you have a smaller activation energy. A smaller activation energy, you'll see a more prominent effect of increasing the temperature. In the old days, they used to say if you have a 10 degrees Celsius, be careful, a 10 degrees Celsius rise in temperature, the reaction rate doubles. But there's all sorts of places where that doesn't happen. So there you go. At any given time, though, lots of molecules don't have the activation energy, so the collisions that they'll have will not form a product. Let's see what we have. We have some summary statements about this here. At any temperature, a larger fraction of molecules can react if EA is small than if EA is large. Good point. For any reaction, a larger fraction of molecules can react if temperature is high than if temperature is low. Fine. Okay. The larger the fractions that can react, the faster a reaction will proceed, the higher will be its rate. Therefore, a reaction with a low activation energy is faster than one with a high activation energy. The rate of any reaction increases with increasing temperature. Now, we can get quantitative about that by something called the Arrhenius equation. Svante Arrhenius, you may remember him from some Swedish guy. He talked about acid-base, Arrhenius acids, Arrhenius bases. We'll get to that in a few chapters. But he also dabbled in the world of chemical kinetics and came up with this equation, which you would be given to on a test. So the rate constant K is some exponential term, which we usually ignore, times E, this part we don't ignore, to the minus EA over RT. So the rate constant is proportional to 1 over E to the activation energy, always a positive value, over R times T. Okay, so if we look at this, we see that if the activation energy goes up, that's the only change we make, then E raised to that gets bigger, so K gets smaller. So if the activation energy goes up, K gets smaller. Now let's look at a temperature increase. If I increase the temperature, not changing the other variables, increase the temperature, R is a constant, 8.314 joules per mole per Kelvin, then the EA over RT gets smaller, and so then you're dividing by a smaller term, so it gets bigger. So temperature goes up, K goes up. So in this equation, A is the value that the rate constant would have if all molecules have enough energy to react. Some people call it a collision factor term or a steric factor. We will rarely use it for anything, that A part. The gas constants are negative sign. We just talked about that. E gets larger, K gets smaller. T gets larger, K gets larger. A varies somewhat with temperature, but in this chapter we'll assume it's a true constant. So I can make a graph by taking the natural log of both sides and I get the natural log of K is the natural log of A minus EA over RT. And I'm going to have a graph here in this example. So you got the natural log of K, which is 1 over T, and the slope is minus EA over R. So if you measure the slope in a graph, and I'm not going to do the graph here, but if you plot the natural log of the rate constant, forget about the units, just take the number, and you plot that over 1 over temperature in Kelvin, of course, then the slope of that is minus EA over R. So once you get the slope, you can get the energy of activation, which has to be a positive value. So what was this question anyways? At high temperature cyclopropane, I did a paper on cyclopropane in 1987, 97, 2007, oh my gosh, 33 years ago. Oh my, okay, whatever, doesn't matter, get back to work. Cyclopropane isomerizes to propene. When this reaction is studied at different temperatures, you get different rate constants. So you're plotting your natural log of your rate constant versus 1 over temperature once it's converted to Celsius, and then you get the slope and you get EA over R. Now, what we do more than graphing, because graphing takes a long time. If it's a multiple choice question on a test, you're going to do 8,000 graphings. We either would give you the slope and you get negative EA over R is that slope, or you would use this 2-point form of the Arrhenius equation. So you look at it 2 points, point 1, K1 and T1, and then K2 or T2. And if you do the math, you get just subtract ln of K2 minus ln of K1. Now, I like to write it like this because that's how most people write it. I don't know why this book is trying to be, thinks you guys are scared of negative signs. But ln of K2 over K1 is minus EA over R 1 over T2 minus 1 over T1. Okay, so that is the more common way to write the Arrhenius equation, the 2-point form, of Arrhenius equation. Okay, so I think we have an example of that. The reaction of NO2 has been studied as a function of temperature. For following decomposition, the rate constant is 2.7 by 10 to minus 2 at 227 and 2.4 by 10 to minus 1 at 277. Okay, so then there's some other thing, but let's do the first things first. So let's calculate the activation energy for the first one. So the natural log, second one listed, will be my K2. So it's a second order process because I know that from the units. 2.4 by 10 to the minus 1 over K1, 2.7 by 10 to the minus 2 equals, what am I solving? Activation energy. So minus EA. EA is going to be in joules per mole, right? Sometimes at the end it's converted to kilojoules per mole, but you've got 8.314 joules per mole, that's a 4. 1 over T2 minus 1 over T1. Okay, get out the calculator here. T2, I got to convert to Kelvin. 277 plus 273 is 550. And T1 is 227. So 227 plus 273 is 500. Okay, so I'm going to do the natural log first. So what is that? That's 0.24 divided by 0.027. Take the natural log of that. Times 8.314, might as well make that negative sign in there. Then divided by 1 out of 550 minus 1 out of 500. And I get 9.99 by 10 to the 4th. By 10 to the 4th joules, or 99.9 kilojoules. and they rounded to 100 kilojoules. Okay, so that reaction where we are going to take NO2 and we're going to break it apart to NO and O2 has to overcome 99.9 kilojoules, or 99 red balloons, to get from the reactants to products. The next one, studies of the conversion of NO2 to N2O4, gives K is 5.2 by 10 to the 8th molarities to -1 second to -1 at both 25 and 87. So K2 and K1 are the same. So it's ln of 1 is minus EA over R, then 1 over T2 minus 1 over T1. Now the temperatures are different, but the natural log of 1 is 0, which means EA is 0. That's interesting. I said before that EA is always a positive number, which is true if you're considering 0 to be a positive number. So all we're doing here is we're just taking NO2s and just smashing them together. So there's just a bond being formed. So they're saying there is no activation energy. Activation energy is 0. There's no bonds breaking, no fancy rearranging. You're just smashing things together. Let's see if they talk more about this. Because bonds must be broken in most reactions, we expect activation energies to be comparable to but smaller than bond energies. I want that to be smaller, but an activation energy of 100 kilojoules per mole, I said 99.9, close enough, is reasonable. Now, this one with a 0. An activation energy of 0 kilojoules per mole indicates that no bonds need to be distorted or broken in the reaction. No bonds were hurt in the making of this screencast. Okay, so you're just forming a bond. The activation energy is 0. Okay. Let's try this for practice. Exercise 1312. I don't know if I did this one before. Let's see. So we got some experimental rates. Let's get the temperatures right away. 327 Celsius. Let me add 273 to that. 327 plus 273 is 600. And the other is 245 plus 273, 518. Okay, so we want to get the activation energy. So the natural log of K2, which is 1 point, this is first order, I know that because the units are seconds to -1. So 1.5 by 10 to the -11 over K1, which is 6.1 by 10 to the -8, is minus EA over R, 8.314, 1 over T2, 1 over 518, minus 1 over 600. So I want to solve for EA. So 1.5 by 10 to the 11 minus, divided by 6.1 by 10 to the 8th minus, take the natural log of that, then times 8.314 negative, divided by 1 out of 518 minus 1 out of 600. Boy, your calculator's getting a good workout there, isn't it? 2.6 by 10 to the 5, 2.62 by 10 to the 5 joules per mole. And you can divide by 1,000, so 26.2 by 10 to the 3. Oh, there's a dog outside. 26.2 by 10 to the 2. That's a 2 kilojoules per mole. So the answer at the back of the book says, yeah, 26.2 kilojoules per mole. And the dogs agreed with that. Okay, let's see. Is this one any useful for us? It says here, if you get the activation energy, you can use the Arrhenius equation to estimate the values of rate constants for reactions where it's hard to get experimental data. So if you know the activation energy and you know a set of rate constant temperature data at one point, you can go to a set where it would be hard, a temperature would be hard to conveniently measure a rate because it's too slow or too fast and use the equation to get that. So here's an example, 1313, lucky 13. Two NO2 molecules collide and react. They can form a bond or exchange an oxygen atom. If they just react to form N2O4, then the activation energy we showed was 0 to a first approximation. But for the oxygen exchange, it's not. It's 100. Oh yeah, like we said before. And the rate constant at 250 Celsius is 8.6 by 10 to minus 2. Did we do that one? Did we look at 250 degrees? No, we looked at slightly different values than that. But okay, they give you that. So they want you to get the rate constant at room temperature. Okay, so let's just look at the answers here rather than reinventing the wheel all the time. So they're telling me that at 250 Celsius, which is 523 Kelvin, my K1, it's a second order process. I know that because the units are molarity to the minus 1 second to minus 1 is given as 8.6 by 10 to minus 2. So that's one set of data. Then I want to get the rate at 25 degrees Celsius. For some reason, it may be hard to measure that for this reaction. 25 Celsius is 298 Kelvin. I'm given the activation energy, so I have to solve. Oh, there it goes again. I have to solve for K2. So, I lost my pen again. Let me go see if I can get. It's good. It works here. But then when I go back to this Microsoft Edge, the lovely Microsoft Edge, the pen's gone. Anyways, follow along with me. I'll just point it out here. So ln of K2. I know that's a signal that this lecture should be over very soon, which it will be. Natural log of K2, and the dog's happy about that. K2 over 8.6 by 10 to minus 2 equals, EA was 100 kilojoules. I better make it into joules because my R is in joules, times 1 over, oh, well, they use positive. EA over R, 1 over T1 minus 1 over T2. I would have done negative and did 1 over 298 minus 1 over 523. Anyways, then you solve for K2. You take the inverse natural log, which is e raised to that power, and you get K2 of 2.4 by 10 to minus 9. Now, you want to make sure that this is a lower temperature, so K2 better be smaller. And it is. It's a heck of a lot smaller. Okay? The immense difference reflects the fact that exchanges of atoms involve a large energy input to break an NO bond. Okay, so that is a good way to look. To always compare things, you know, does it make sense? If it's a lower temperature, you're going to have a lower K value. And you can try 1313 practice exercise on your own. Most reactions have activation energies of around 100 kilojoules mole per greater when the reaction is exothermic. And hydrogen and oxygen, well, they can sit pretty and not react at all because of the strong bonds that have to be broken to transform hydrogen and oxygen into water molecules. Strong bonds result in a large activation energy. Now you'll get the explosion when a spark is applied to a mixture of hydrogen and oxygen. Spark gives some of the molecules enough energy to overcome the activation barrier, and after the reaction starts, whatever energy is released as water molecules form raises the temperature sufficiently, and the reaction keeps on going. Okay, so lots of reactions have large activation energies, not all of them. You can read through that. There's a picture of it. Kinetics of SN1 and SN2 reactions on page 650. We don't discuss that one. So catalysis, that'll be our last unit. We'll start the last lecture, and we'll start that next time. Okay, so have fun with all of that.